Good morning, sir. Professor Bala.
Good morning,
Very good morning.
Professor Bala. Good morning. Yeah.
Good morning, sir. Professor Satish.
Yeah.
Good evening.
Good
Good evening.
morning. Good morning. Good morning. Yeah. Devendra. Yeah. Good morning.
Good evening, Dr. Balakrishnan. Good evening from India. I think you have muted it. Your mic is mute.
Can you hear me?
Yeah, now you can hear. Yes.
Yeah. It's early morning here. How are you?
Going on well, sir, as usual. Very nice to meet you again.
Nice to see you again.
Yes. This is an occasion that we celebrate always.
Are you in Chennai or in Kumbakonam?
No, I am in Kumbakonam.
Kumbakonam, okay.
Come this side one time whenever you come to India.
I have not come to India for 2.5 years now due to COVID. In fact, I am planning to visit in this February to April period once.
Please, remember us, and we are here. Whenever, if you come to this place, part of the India, please.
Certainly.
We are
Yeah,
planning.
I want to make a trip because I want to go and see my birth town, Mannargudi.
Yes. There are people around. We can go and stay. No problem. Please come.
Yeah, not too far from Kumbakonam, actually.
Yes. Not far. It's 1 hour from 1.5 hours.
Yes. Mhm.
Hello, Professor.
Hello.
Hello, Professor.
Yeah.
Satish Kumar is here. Yeah.
How are you, Satish Kumar?
Yeah, fine, Professor. Fine.
Good.
Yeah. 11, sir. How is the Professor Bala? What about their everything?
Good evening.
Kalyanam, sir.
Good evening, Satish.
Good evening, sir. Good evening, sir. Sir, okay. Was there any problem with the camera? No. Oh, okay. There is a little more light is needed for you. I think uh, so I think let us start the program with a formal inaugural function with a 10 minutes maximum, 10 minutes. So this is the 8th international workshop conducted along with as a pre-conference workshop. Respected professors from various parts of the world and respected and their delegates, those who are interested to join with these events. In fact, we are very lucky to have several well-known experts in the area of distribution theory, especially our Professor Bala, the giant in the area. And in this occasion, we have our Kalyanaraman sir, our former professor of our department, and my guru is also with us. And Kalyanaraman sir is popular among the group of, especially the statistics fraternity in India. And he is in fact is a lighting force for us because of all the event, whatever he will always with us as a leading force, leading light. And with the blessings of our great gurus like him and our ancestors, I would like to invite Kalyanaraman sir to say a few words as an inaugural address, and so as to inaugurate this international workshop. Welcome, Professor.
Thank you, Dr. Satish. It's always a pleasant exercise to be part of the functions of the Department of Statistics, University of Kerala, which I have been associating over the last 60 years of my existence. And I feel highly proud of my department for those who are manning the activities of the department have brought in some kind of a tradition as far as conducting seminars and international conferences like what you are going to see in the next few days. And also they conduct a workshop before the conference, very usually. And for the last 2 years, I think that they are bringing very high people and to have some discussions on current topics of interest of the department. And why I say it's a tradition, in Trivandrum, apart from all other social and religious functions, there are 2 functions which are happening every year, associated with the Padmanabha Swami temple in Trivandrum. That is a festival in the month of Aipashi and a festival in the month of Panguni. There are two festivals which are regularly being conducted. It's a tradition in the department, the city of Trivandrum. Similarly, this is the 8th edition of the international conference, I think, which they are conducting over the last 7 years, and this is the 8th year. And this tradition is getting settled because this is going to happen for many more years to come. I hope and wish that this continues for perennially without any end to that. So that kind of a culture has set in, and I appreciate all my I would say colleagues and students who are manning the department currently, and I hope to be of any help to them as far as the conduct of such functions. So it's a very happy occasion, and apart from that, we have our Dr. N. Balakrishnan to inaugurate the initial speech associated with the workshop. And I have been yearning, actually, for the last few days, I have been wondering what is happening, because I got the message only very recently that the function is going to happen on the 13th last month, I suppose. Until then, I was just yearning, maybe it's another occasion for me to hear Dr. Balakrishnan, and it is happening now. Sir, please continue to be associated with us for years to come, and don't leave us. And I just pray and request you, as the senior most member of the faculty of the Department of Statistics, University of Kerala, and I wish the entire function and the proceedings to go for a very successful completion for the next few years. With all prayers, I now invite Dr. N. Balakrishnan to deliver his talk on the topic of the distribution that he has chosen. Okay, sir, thank you. Mic over to Dr. N. Balakrishnan.
Thank you very much, Dr. Kalyan Raman. Thank you very much for Dr. Satish Kumar for arranging this fine event on a regular basis, and also for including me in the program.
Just a word, Professor.
Yes.
Thank you, Kalyan Raman sir, for inaugurating this function. And before starting the session by Professor Bala, as usual, our students, Professor, I think student Adira is ready to introduce in their own way. Professor Bala. Just a few words. Okay, thank you. Welcome. Adira, please.
Welcome all. I hereby invite Professor N. Balakrishnan, Department of Mathematics and Statistics, McMaster University, Canada. Professor N. Balakrishnan did his PhD in statistics from IIT Kanpur. He was the past president, International Indian Statistical Association. He was the elected member of the International Statistic Institute in 1992. I hereby welcome Dr. N. Balakrishnan, sir, to please chair this session.
Thank you very much. It is a pleasure to be here, and also I want to thank Dr. Satish Kumar for including me in the program of the conference. Until yesterday, I was not sure whether I could take part in it. I have lots of exams, more than 250 exams on my desk for grading. So I took this early morning hour to make a presentation. I'm going to talk using two files. I hope I don't have any technical trouble in finding the second file. I want to first introduce, let me see whether I can get can you see the slides? Yes?
Yes, sir, yes.
Yes, we can. It is okay.
I'm going to first give a little introduction to, because it's a distribution theory workshop, I want to introduce some of the pioneers in the area. And I have had the great privilege of working with a few of them, including Professor Kotz. If Kotz was alive now, he would have traveled to India with me. He would have been over 90 years old. And he passed away about a dozen years ago. And I have worked on this generalized version of Dirichlet distributions. Over the years, I have written a few papers. Now I am going back in time to look at this model to make further work. So I thought it will be an appropriate an opportunity to discuss about this model. And first, I want to introduce to you all of you what Sam Coates is all about and who he is. This work is actually with one of my co-authors, Enkeleid Ashorba. He is at University of Lausanne in Switzerland. We wrote a couple of papers. Both of them appeared in Journal of Multivariate Analysis about 10 years ago. Since then, I have written many papers. So I'm going to give you an appraisal of what the model is, what it is all about. But before I do that, I thought I should introduce to you my co-author, Samuel Coates, who is no longer with us. He died in 2010. And he was an interesting personality I met in early in 1990 when he was visiting McMaster University. Then we started collaborating on various projects. So I want to give a little historical detail about Sam. And many of you know about the books of Samuel Coates. So I thought it would be good for you to know the man behind the name. Sam was born on August 28, 1930. Contrary to people who think that he was born in Russia, he was actually born in China, in Harbin. He was the only child of Boris and Guta. Her original name was Kahana Coates. His father was of Russian origin. He was an engineer associated with the railways that were being built up at that time. It is now called Trans-Siberian Railway. His mother was not of Russian origin, but of Polish origin, stemmed from a famous rabbi family in Warsaw, and was a highly educated person. Sam was very close to him. She instilled in Sam deep appreciation of education and scholarship. At the age of 87, even in her deathbed, she still fluently and lucidly conversed with visitors in 7 different languages. Her first language was Polish, second language was Russian. She was fluent in Chinese and Hebrew, among them switching easily from one to another. Sam naturally inherited the strong interest for languages from his mother, and he could speak and read in 11 different languages, which was remarkable. He could speak and switch from French, German, Italian, Yiddish, etc. He graduated in 1946 with honors from the first Russian school that was established in Harbin. He then studied electrical engineering in the Harbin Institute of Technology. It is one of the top educational institutions in China. He studied in 1947 to 1949. So in 1949, he emigrated with his parents to Israel, where after 2 years of military service, he studied at the Hebrew University of Jerusalem. He obtained his MA in mathematics with honors, with minors in physics and statistics in 1956. He often used to comment that he got his MA the same year I was born, 1956. He subsequently served 2 years in the Israeli Meteorological Service, and then in 1958, he went to Cornell University, the graduate school, and obtained his PhD in mathematics in 1960, 2 years later, with a specialization in mathematical statistics. So 4 years following that, he had research positions at the University of North Carolina, at Chapel Hill and University of Toronto, where he established 2 major relationships. One of them was a professional one at University of North Carolina with Norman Johnson. Another one was a personal connection with his wife, who was a student at the University of Toronto. In 1964, he joined as an associate professor at the University of Toronto. Then in 1967, he moved to Temple University at Philadelphia as a professor of mathematics. Then in 1979, he moved to University of Maryland at College Park, and he served there until his retirement. After retirement from there, He joined as a professor emeritus at George Washington University until the end of his life. He held visiting professorships in more than 15 universities across the continent. He had positions in USA, Canada, UK, Sweden, Denmark, Hong Kong, and China. He was elected as a fellow of the American Statistical Association and Institute of Mathematical Statistics. He was an elected member of the ISI, and he was awarded an honorary doctorate degree from the University of Athens, Greece. He authored numerous research articles, more than a couple of hundred articles, and he wrote many books. Included in this impressive list of books and articles are 5 volumes of Distributions in Statistics, co-authored with Norman Johnson. The discrete distribution volume was revised with Adrian Kemp, and the continuous univariate, multivariate, and discrete multivariate with myself. We also edited 14 volumes of Encyclopedia of Statistical Sciences, 3 edited volumes of Breakthroughs in Statistics, and he also authored a book on multivariate symmetric distributions with Kai-Tai Feng and Ng. That book is particularly important for my presentation today. Sam was married for 46 years to Rosalie Coates, whom he met in Toronto in 1963 and subsequently married in 1964. Rosie, we all called her Rosie, was a keen supporter of Sam's intense academic life and often helped him by doing typing, proofreading, arranging his travels, etc. They have 2 daughters and a son and 2 grandchildren. Sam was very active in synagogue and in the teaching and popularization of Yiddish as a language, and in fact translated many popular books from other languages to Yiddish. This is something that he would always do in the weekend on Saturday and Sunday. Sam Coates was truly a doyen in the field of statistics in every sense of the word, and he was one of those personalities who influenced me greatly and developed and nurtured my interest in distribution theory. So it is therefore my great honor and pleasure to dedicate this talk in the memory of Samuel Coates, who left this world about 12 years ago. And he was a close personal friend of mine, family friend of mine, and his family is close to me, and I miss him dearly. So I wanted people to know what kind of stature he had in the profession and what kind of a personal life he led and what kind of contributions, diverse contributions, not only to statistics, but to theology, religious studies, Yiddish language, etc. So with that, I'm going to start. I'm going to start the technical talk. Let me see whether I can get back to my window. Oh. Can you all see this window?
Yes, sir.
Yes. I'm going to make it as a full screen, and I'm going to talk about Pearson-Coates-Dirichlet random vectors. And this is a talk that I just prepared. This is, even though some of the work that I am presenting is 10 years ago, published in a series of papers in Journal of Multivariate Analysis, I am going to, towards the end of the talk, give some results which are more recent results. Some of these are related to my current work going on with Chris Jones. We have done some work on univariate beta and mixtures of beta, mixtures of Dirichlet, and I may touch upon towards the end of the presentation. So this is called, there is a typo here. It should be Pearson-Coates-Dirichlet random vectors. I'm going to talk. This is the table of contents of this talk. I'm going to first introduce Dirichlet random vectors in L1 space. Then I will go from Kautz to Pearson-Kautz Dirichlet random vectors. And this is directly connected to multivariate students T distribution. And I am going to present some stochastic representation. These stochastic representations enable us to establish several distributional properties and some asymptotic results. The asymptotic results I'm going to talk about are like tail behavior and tail index and about the thickness of the tails, etc. And the distributional properties, surprisingly, mimic some of the properties that we already know for elliptically symmetric distributions, elliptically contoured models. And this is how Samuel Kautz's work, pioneering work on elliptical distributions, come into play. I have done some work on statistical inference for these models, such as maximum likelihood estimation, EM algorithm for fitting, etc. And I have studied in a series of papers in Journal of Multivariate Analysis, multivariate measures of skewness and kurtosis for these models, but I won't have time to go over all those details. So I will stick to these 5 topics and introduce, in particular, this is a workshop, so I'm hoping there are a lot of students, so you should know some of the basic multivariate constructions and models, and this will give a preamble to what you are going to learn from other experts who are going to make presentations in this workshop. So first I'm going to talk about a uniform distribution on the simplex. What I'm going to do is use a bold letter to indicate that they are vectors and the ordinary Roman letters to indicate that they are components of the vector. So the vector E, they are always a column vector. So E is a k-dimensional random vector, E1, E2, Ek transpose. E is a notation that I have introduced because they are standard exponential random variables. I constantly use the notation equal to in distribution. That means it is equality of distribution functions. So if I put X equal to Y, that means they are equal in distribution. I'm going to introduce a random vector O. Once again, it is a column vector of dimension k, O1, O2, OK transpose, and O denotes it's a uniform distribution on the simplex. What is a simplex? X1, X2, Xk is a k-dimensional non-negative vector, component vector. Xi's are positive, but their sum is equal to 1. So it sits on the hypersimplex of k dimension. So this is clearly a k-dimensional uniform random vector, but the actual dimension of it will be k minus 1 because it has a linear constraint summation xi equal to 1. If I now take the original exponential random vector E1, E2, Ek and consider a transformation as E1 divided by the sum of the EIs, E2 divided by the sum of the EIs, Ek divided by the sum of the EIs, then this is what is called as uniform distribution on the simplex. So this random vector O has exactly the same distribution as E1 divided by the sum, Ek divided by the sum. And in particular, notice that these O1, O2, OK are all dependent. Why are they dependent? The numerator E1, E2, Ek are all independent, but they share the same common denominator. The common denominator is the sum of the EIs. And what else do you see? The denominator is always larger than the numerator, and hence you have xi's to be positive and it is less than 1, the sum of them will be equal to 1. And in particular, if I focus on one particular component, let us say ith component. Ith component will have ei, which is an exponential random variable in the numerator. Denominator will be the sum of exponential random variables. Exponential is a particular case of gamma with shape parameter 1. So the numerator ei is a gamma random variable with shape parameter 1. The denominator is a sum of independent exponential. So it will have a gamma distribution with parameter k. So the ratio will be distributed as a beta. This is the famous result of Rao from 1943. So OI has distribution beta. The numerator has a gamma with 1 degree of freedom, so beta 1. Denominator is the sum of gamma 1 and gamma k minus 1, so it will have a beta 1 k minus 1. So this follows by the independence of the exponential random variables ei. This result has been presented in multitude of ways, but I like to think of the connection between beta, uniform, exponential, and gamma using this uniform distribution over the simplex. Lot of variations of this result has been presented. In fact, this beta result, if there are many variations that we can present. There is a paper just this year, a few months ago, by Balakrishnan and Jones, Statistics and Probability Letters, where we present many different variations of this beta construction using gamma and exponential. People who want to play around with this construction can look at this paper in one of the recent issues of Statistics and Probability Letters. So, E1, E2, Ek, as I said before, are IID standard exponential. So, another representation we can give is, I have given here, starting with E, I have constructed a uniform distribution as ratios. But we can also think about another representation, a stochastic representation for the random vector E, which is an exponential random vector. I can present it as the uniform vector O1, O2, OK multiplied by a random variable E, R. What is R? R, I am going to make it as the sum. Remember that E1 divided by the sum, E2 divided by the sum, Ek divided by the sum. What do we know about the sum? The sum are nothing but a gamma random variables. We also know the ratio is always independent of the denominator. In fact, this is one of the elementary result on distribution theory we present. If x is gamma alpha, y is gamma beta, and if they are independent, x over x plus y is beta alpha beta, and it is independent of the denominator x plus y. So I can use that result, rewrite, express, make a stochastic representation for an exponential random vector as O1, O2, OK, which is a uniform distribution on the simplex, multiplied by an independent random variable R. The R is nothing but a gamma distribution because it is just a sum of independent exponential. So if I want, for example, characteristic properties, etc., I can use this and think of this R as a mixing random variable. So O1, O2, OK are the uniform random variables on the k-dimensional simplex, and they get mixed with a gamma random variable, and that gives rise to independent increments, E1, E2, Ek, which are exponential random variables. So now I am ready to introduce to you Dirichlet distribution on L1 space. So if I think of R as an independent random variable, independent of O, it's a positive random variable, then I have the random vector X to be distributed as R times the random vector O. O is the uniform simplex distribution in k dimension. R is a non-negative random variable with probability 1, and it is independent of O. This is a mixture. It is a mixture with a mixing distribution of R. This is what is called as Dirichlet distribution in L1 space. In particular, if I take I1, I2, Ik to be Bernoulli random variables, Bernoulli random variable are not 0, 1, but instead I take +1 and -1. So if I take I1, I2, Ik to be Bernoulli independent random variables plus or -1 random variables, then if I think of the random vector X, which is mixed with these Bernoulli random variables, I'm going to have I1 times R, the first component of O, which is O1, Ik times R, the kth component of O, which is nothing but I times O. So what I will have is, remember that RO has the same distribution as X. I call this as IO. This is not producing indicator variables, and I am multiplying the R with respect to O. These are called weighted L1 Dirichlet random vectors. A historical remark. Why is it called a Dirichlet random vector? In fact, the Dirichlet distribution on the hypersimplex, the uniform distribution on the simplex, was first appeared in the work of Johann Dirichlet. Johann Peter Gustav Dirichlet lived a short life for 54 years. He was a German mathematician, most well known for what are called as Dirichlet series. He also did a lot of work in analysis. So the distribution which is associated with Dirichlet integrals or Dirichlet series is called as a Dirichlet distribution in his honor. So I am now going to introduce copulas, which are called Archimedean distributions or Archimedean copulas. So take U, U1, U2, UK, and I think of UI to be a marginally a uniform distribution on the interval 0 to 1. Distribution of U usually is given in terms of what is called as a copula generator, phi. What do we know about phi? Phi is always a positive function, and it is a k-monotone function. A k-monotone function simply means that I should have some condition satisfied by its derivatives, up to k-2 derivatives. So if I now think of phi as a monotone function making a transformation on the component ui, then if I take the inverse function of the generator phi, because it's a monotone function, its inverse exists uniquely, phi inverse of summation phi of ul for L less than or equal to k will define the marginal distribution function of u. So if I take, for example, L equal to 2, I will have phi inverse of phi of u1 plus phi of u2. That will give me the marginal distribution function of u2. So I can construct the marginal distribution function purely in terms of the generator phi. One of the nice properties of Archimedean copulas is that this generator satisfies a lot of nice properties, and that is therefore useful in the construction of several distributions. So the probability density of the Dirichlet random vectors. Remember the Dirichlet random vectors that I introduced, the L1 Dirichlet random vectors? I'm going to talk about what is the probability distribution of the component. Remember, I have the uniform simplex multiplied by an independent random variable, which is positive. It's a mixing distribution. So I need to derive its distribution, and the distribution or the density can be derived using this Archimedean cupola principle. If the radius r possesses a probability density function, then the random vector x will have a probability density function given by the density function of x1, x2, xk, the k-dimensional vector, will have a gamma k as a normalizing constant. It will be a function of summation xi. So that means summation xi acts like a sufficient statistic in this case. Everything can be summarized in terms of summation xi, multiplied by summation xi to the power 1 minus k, where xi's are positive, I less than or equal to k. So this f therefore plays a critical role in the density function of x. In particular, let us take the probability density function f of the radius r to be a Erlang distribution. Erlang distribution is nothing but a gamma distribution with the integer parameter k. Then h of x1, x2, xk, this is just a gamma distribution, a gamma density with the integer parameter k that will immediately reduce to e to the power minus summation xi. And that is nothing but x as independent unit exponential components. See how I have constructed a connection between I started with the independent exponential random vectors, took transformations to introduce a uniform on simplex. Then I mix the uniform simplex distribution with a radius r. It can take any non-negative distribution or as a density f. And then I introduced Archimedean cupola. This f is going to be connected to the generator of the Archimedean cupola. It shows that if I choose a particular f as an Erlang distribution, I go back to my original construction that x has independent unit exponential components. And is this unique? In fact, the form of the PDF of Dirichlet random vector, its survival cupola is Archimedean. So you can ask the reverse question. Suppose I have an Archimedean cupola as a survival cupola. Is the distribution of L1 Dirichlet leads to exponential? The answer is yes. There is a paper by McNeil and Neslova in which they talk about uniqueness, and the converse also is true. In fact, you can assume an Archimedean cupola, use a Dirichlet random vector, the inverse transformation will lead you to independent exponential components. So they all tie together. Now, I can go from L1 space to LP space, and I'm going to define a LP Dirichlet distributions. And both the LP and weighted LP Dirichlet random vectors can be readily introduced. If I have a distribution that I have defined in L1, it is very easy for me to think of how to construct a LP version of it. So I'm going to start again the construction. I'm going to assume as before epsilon I or ei to be exponential random variables, and I assume that ei to the power p are gamma random variables with the parameters alpha I and 1 over p. So I will have the so it is epsilon I to the power p now takes a gamma distribution with parameter 1 over p and alpha I. Now you do same transformation as I did before. Earlier I took exponential divided by the sum of the exponential. Now I am taking epsilon I to the power p to be gamma random variables. So these are gamma and they have a power 1 over p. So I take a power 1 over p. So in the denominator, I have the sum epsilon I to the power p, whole thing raised to the power 1 over p. So these guys are dependent, even though the numerators are independent, but the denominators are common. So O becomes a dependent random variable. What random vector? What kind of condition it has? Almost surely, if I raise these components to the power p, I will have epsilon 1 to the power p, denominator 1 over p and p will cancel. I will have the sum of epsilon I to the power p. So the numerators will add to the denominator. So there is a constraint, except it is not a L1 constraint, it is a LP constraint. Earlier I had the sum of the variables OI's to be 1. Now I have the sum of OI to the power p to be equal to 1. So this is called the P norm. Remember, P norm is a norm only for p bigger than or equal to 1. So the lowest I can go in terms of p is 1. That is why I started with a L1 norm Dirichlet distribution. So once I have a L1 norm, I know how to manipulate it to construct a LP norm distribution through gamma and raising it to the power 1 over p. So this gives a flexible family of distributions, and I can do modeling with it. I will take an example. The example is a familiar L2 Dirichlet random vector. So L2 Dirichlet random vector means I'm now going to deal with L2 norm. So I'm going to take p to be equal to 2. So that means I am squaring the components. You can immediately see that this is going to be related to something like a chi-square. So I have a L2 norm, in which case I take p equal to 2 and alpha i's to be equal to half. Why alpha i's are equal to half? Because when I take the gamma random variable, p times alpha I will get them to be of mean 1. So they are all balanced to have mean 1. And I'm going to take, as before, I1, I2, Ik as IID Bernoulli random variables, and these guys take values -1 and +1, so they take a value of mean 0. Then a weighted L2 Dirichlet random vector X in Rk, I will have the parameters alpha I in L2 has the stochastic representation X. I will take the vector O that I introduced before. This is the vector O in P norm with P equal to 2, and I will mix them. That means with a positive with a half as a probability, I will make the component positive, or half as a probability, I will make the component negative. So I introduce now in R square. So I will have R as a radius, R square, that is R to the power k. Remember, P R to the power p. P is in this case is 2. So R square has a gamma distribution with parameters k over 2.5. What about R, I, and O? They are all mutually independent, and IO is uniformly distributed on a unit sphere, and I will have the squared norm equal to 1. So it follows that X is a Gaussian random variable with IID components, and that is the construction and the stochastic representation as a mixture. Here the mixing distribution is R. Do you recognize this distribution? I can, since I have a special case of gamma here, I can connect it to Kautz-Dirichlet random vector. The Kautz-Dirichlet random vector works like this. The random vector epsilon with independent components epsilon I, such that the pth power of epsilon are all gamma random vectors with parameters. Remember, in the previous construction, I took all the alpha i's to be half. But instead, I now take random alpha i's and 1 over p as the second parameter. This is what is called as LP Kautz-Dirichlet random vector. In this case, the stochastic representation for X is nothing but the mixing random vector R multiplied by the vector O. R is independent of O. R to the power P has a gamma distribution. It's a sum of independent gamma with the different shape parameters and the common scale parameter. The scale parameter is 1 over P. The shape parameters are alpha 1, alpha 2, alpha k. So the sum of them will give me gamma alpha 1 plus alpha 2 plus alpha k and 1 over P. So R is independent of O. This is a mixture representation for Kautz-Dirichlet random vector. In particular, if I put all the alpha i's to be 1 over k, I will get the usual Dirichlet random vector. So, I can prove many properties that I can for this Pearson-Kautz-Dirichlet random vector. The Pearson-Kautz-Dirichlet random vector is a transformation, and it is a transformation with a coefficient matrix A. A is a k by k real matrix. Epsilon is a k-dimensional Kautz-Dirichlet random vector that I introduced here. Remember that this is the Kautz-Dirichlet random vector. It's a mixture of O, which is the Dirichlet random vector, and it's mixed with a gamma random variable R. And I can now take epsilon to be a k-dimensional Kautz-Dirichlet random vector. It has k parameters alpha 1, alpha 2, alpha k, and P. X is said to be a Pearson-Kautz-Dirichlet random vector if X is distributed as R epsilon, which is the same as here, and now I put a coefficient matrix A. R is independent of epsilon, but it is such that if I raise R to the power P, it has the same distribution as a reciprocal gamma. Some people call it as an inverse gamma. So lambda over, excuse me, it will be a gamma random vector with the parameter theta and 1 over P as the parameters. So we can introduce a weighted Pearson-Kautz-Dirichlet random vector. The weights I introduced the same way. Remember that all these distributions are sitting on the positive space. If I want to fill my R to the k, that means a whole real line in k dimension, I have to mix them. I mix them with equal probability. So I can take -1 and +1 and mix them. If I mix with equal probability, I will end up with a symmetric random vectors. I can also give different probabilities, in which case I get what are called as skew-symmetric models. So I is a k-dimensional random vector and Bernoulli plus or minus 1 component with equal probability. Then if I take X distributed as IE, that's a mixed Dirichlet random vector multiplied mixed with a random variable R, which has an inverted gamma and a coefficient matrix A. This is called the weighted Pearson-Kautz distribution. Epsilon, I, and R are mutually independent. So you assume that the random vector I has symmetric component, but you don't have to. You can even put asymmetric Bernoulli random variables. It will produce tails, skewness on the right, skewness on the left, depending on how much probability you put on the left and how much probability you put on the right. So this is a very general construction of distribution. Now, I want to connect it to students' distribution, multivariate students' distribution. A k-dimensional student T random vector, we know it's a scale mixture of a k-dimensional zero mean Gaussian random vector Z. So we know the multivariate students T distribution has the same distribution as a multivariate zero mean Gaussian distribution mixed with the square root of V. What is V? V is such that lambda over V is gamma distributed with parameter theta over 2.5. So standard choice, you choose theta and lambda to be equal to k. This will give you a multivariate student's t distribution. You can see that this is directly related to the Kautz-Dirichlet, Pearson-Dirichlet distribution that I gave. And all I have done is dropped, for example, all other components, taken V to be the inverse gamma that we talked about before. I can do spectral decomposition of this vector. If Z has covariance matrix sigma, I can write it as AA transpose, then X will be distributed as A, that is my A matrix coming from here, AA transpose UV decomposition, A, square root of V, V is the inverted gamma random variable, times Y. What is Y? Earlier, I had a zero mean Gaussian random vector, which is a colored noise. By this decomposition, sigma equal to AA transpose, I have now constructed IID Gaussian components. What do you see here? X is distributed as some vector times IID Gaussian components. This is the mixing vector. The mixing vector is A times the matrix A coming from the spectral decomposition times inverted gamma random variable. And this Y is IID standard Gaussian components. So, Pearson type 7 random vectors. You can also introduce generalization of student T random vectors. And these are called Pearson type 7. Those of you who know Pearson system in the univariate case, if you look at Pearson type 7, it is a generalization of student's T distribution. So you can construct a multivariate version of Pearson type 7 random vectors, and this was originally given by Gupta and Song in 1997. They introduced LP, Pearson type 7 random vectors. How do I define LP Pearson type 7 random vectors? You start with a Y, which is a k-dimensional standard Gaussian random vector with independent components. Remember that I can always do the decomposition sigma equal to AA transpose, and I can take AY. So I have standard Gaussian random vector with independent components, and I have the absolute Y on the numerator. The denominator, I take the squared norm, absolute Y square, has the uniform distribution on the unit sphere. Because I took the absolute value in the numerator, this will always be 0, and I will have the squared norm in the denominator. It's going to go from 0 to infinity in the k-dimensional space. So you denote by O a LP Dirichlet random vector with a constant radius r. Then r equal to 1, for example, without loss of generality. Then O distributed as, because I have taken r to be equal to 1, r epsilon will become simply epsilon. So it will have epsilon divided by, remember that the p at the norm is the sum of epsilon e I to the power p raised to the power 1 over p. So if I look at this mod of y, it is nothing but epsilon. Denominator, norm of y square, is nothing but the norm here. So if I take p equal to 2, I will end up with norm of y square. If I take absolute y to be epsilon, the job is the same, the construction is exactly the same. So the role of absolute y for p equal to 2, alpha I equal to half, is played by the random vector epsilon in my original construction. When p is bigger than 0, alpha I is bigger than 0. So this tells you that the Pearson type 7 random vector generalization of student T is just a particular case. All I have to do is interpret what the numerator is as an epsilon, what the denominator is as a metric, as a norm. So, a historical remark, why I call that as called Pearson's, because Pearson wrote his famous paper in 1902. It is a paper on the Pearson system of distributions, where he introduced a whole bunch of distributions, all in univariate case. And he gave his famous, what is called as a Pearson diagram. He explained what region of the coefficient of skewness and kurtosis all these Pearson families of distributions occupy. So the Pearson is a pioneer on the statistical distribution theory. So I say here, Carl Pearson, British statistician, he lived about 79, 80 years old, who made many path-making contributions to statistics, and especially laid the foundation for distributions in statistics. Most of the distributions that we study now, for example, beta, gamma, students T, chi-square, etc., were all present in the original pioneering work of Pearson. So I now talk about a Pearson-Dirichlet random vector. A Pearson-Dirichlet random vector X will correspond to, remember, O is my original random vector that I started with, is a uniform on the simplex, k-dimensional simplex. R is a radius, it's a positive random variable which can have a distribution that's independent of O, and A is some matrix of constants. So that's like scaling. So you have R times O, A is a scaling variable. So with R being independent of O, and if I now take the pth power of R, because I am dealing with pth norm, pth power of R, it should have the same distribution as lambda times, lambda is a scaling constant, W tilde divided by W. Remember what is W tilde and W? W tilde is just one of the gamma components in the numerator. W is the sum of the gamma components in the denominator. So the numerator is always smaller than the denominator. So this W tilde divided by W is always in the interval 0 to 1. If I want to make it 0 to infinity, I have to scale it by lambda. So this lambda are the scaling constants. So W tilde, you remember that I mentioned earlier that if I take an independent gamma with alpha divided by gamma with alpha plus gamma with beta, it has a beta distribution and it is independent of the denominator. Therefore, I should have W tilde divided by is independent of W, and W has a gamma with the parameter theta and 1 over p, and W tilde has gamma of the sum. So this gamma theta 1 over p, the 1 over p is common. It is a p for giving us the p at the norm. Theta is just a scaling scale for the corresponding gamma random variable. So this is a Pearson-Kautz-Dirichlet random vector as introduced before. This is the most general form. Remember that this is a mixture. So in order to study the moment characteristics, the tail behavior, I don't have to mess around with the density function. I can just use this representation. I will have X to be Pearson-Kautz-Dirichlet random vector. It has a coefficient matrix A, k by k positive matrix, alpha, which corresponds to the shape parameters of the gamma distribution components. P is the pth norm. Lambda is the scaling constant corresponding to R. Theta is the numerator. Remember that gamma in the numerator is independent of gamma in the denominator. So I take a gamma divided by a gamma random variable. It has the same scale, and they will be independent. They will be this W and W tilde are independent. Ratio will be beta distribution. So that's a construction. Now I am going to introduce some notation. In order to manipulate the distributions and to establish some properties, I need to create partitions. I take the set of numbers 1 to k, and I consider I and j to be partitions of this. A is a k by k real matrix, which is a coefficient matrix. I take xi is the set of coefficients xi is a subvector of x with respect to I. Then aii will be the submatrix of A. Aij will correspond to the coefficients of the matrix A with I and j belonging to the partitions I and j. So I have aii, aij, aji and ajj are submatrices of A. Whenever I use a bold 1, it means it's a vector of ones. Whenever I use a bold 0, it's a vector of 0, k-dimensional vectors. Alpha is my vector of alphas coming as the shape parameter of the gamma distribution components. Alpha 1, alpha 2, alpha k, and we know that they have to be positive. So it's 0 to infinity, kth space. So now I'm going to give you some basic properties of student's t distribution. But usually the properties of student's t distribution are derived from the characteristic function of student's t join density function of student's t. It's a messy calculation. But I'm going to give you simple properties just from the stochastic representation that I gave in the previous page. All I need is a stochastic representation. I can prove all the properties that I need. So I'm going to start with x, which is a k-dimensional random vector. It has a student's t distribution. And think of an underlying covariance matrix sigma for the random normal vector, which has a UV decomposition as AA transpose. So sigma is a positive definite matrix of full rank. Then in our notation, X has Pearson-Cotes-Dirichlet distribution. It has the coefficient matrix A, and I will have the vector half, 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 half. So the vector 1 divided by 2, and I am looking at the P norm, which is 2, and theta is the component of the shape parameter of the numerator gamma, and the scale parameter is theta over 2. All the alpha i's are half. So the student's random vector, student's t, random vector x, has very interesting distributional properties. What is the property? The first one is the marginal distribution of x are all student t. How do I know? From the very construction. Because the construction takes the ratios which are independent, and you automatically get a normal divided by a gamma. Gamma is nothing but a chi-square, square root pth norm. So it's a square root of a chi-square. I get student's t automatically. This is what I call as a free B. The conditional distribution of xi given xj. Remember what are xi and xj? They are partitions. So there is no element in common. If I look at the conditional distribution of xi and xj with I and j as disjoint index subsets of 1 to k. So it doesn't matter what the dimension is. I may be 3-dimensional, j may be k minus 3-dimensional or less. But they have to be disjoint. There is no common element. Is again student's t distribution. Moreover, we automatically get x to be an elliptically symmetric random vector. So that means a student's t distribution for all its degrees of freedom is elliptically symmetric. If you make a contour, contours will always be elliptic in nature. And in particular, you will get a normal distribution as a particular case. So an elliptically symmetric random vector with a positive random variance R has the stochastic representation x equal to the radius R, which is a positive random variable with some density. O is nothing but the uniform distribution on the unit simplex that I started with. A is the matrix that is coming from the positive definite matrix sigma, which is written as AA transpose. So this elliptically symmetric random vector always has the decomposition, a radius random variable with some density f, and it is positive random variable. A corresponds to the root of the sigma matrix, and O is the uniform distribution of the simplex in L2 norm. So R being independent of O, uniform distribution on the unit sphere L2 norm of Rk, and A is a given K by K real matrix. If I take B to be another K by K real matrix such that B equal to B transpose has the same distribution as AA transpose equal to sigma, then you notice RAO has the same distribution as RBO. That means the distribution of X is only determined by the matrix sigma, and it cannot be determined by the matrix A. So, for a Dirichlet random vector, however, if I consider a Dirichlet random vector in particular, this is not the case. A determines its distribution and not sigma. But in general, if I consider an elliptic symmetric random vector, the sigma matrix is the only matrix that determines the distribution of X, not its root. And that's an important property and distinction between Dirichlet and elliptically symmetric distribution. So the Dirichlet distribution, even though is similar in principle to elliptically symmetric distribution, differs in this way significantly in terms of parameterization and characterization. So we can put a theorem now. The theorem says X is a Pearson-Cotes distribution random vector with matrix A, shape parameters of gamma alpha, P norm, lambda theta, and I have a k-dimensional random vector. A is a non-singular K by K real matrix. If I is a subset of 1 to K with M elements and J is the rest, that means it is a difference of 1 to K from I. Further, AJI, that is the matrix A corresponding to J and I as the elements for these two sets. If they are all 0, then Xj has to have a Pearson-Cotes Dirichlet distribution. If so, this what it proves is that if I look at the matrix A such that the disjoint subsets of I and J, the corresponding elements of A are all 0, then if I have X to be Pearson-Cotes Dirichlet, the component Xj will also have Pearson-Cotes Dirichlet distribution, subject to this condition. If X is an elliptical random vector, then the condition AJI has all its element to be 0 can be dropped, since AA transpose determines its density completely. But in general, you can do, provided this condition is satisfied. So this is a stronger result than what is known for elliptically contoured random vectors. Conditional distributions we can talk about. I have talked about the marginal distribution of Xj. Let us look at the conditional distribution. If X has Pearson-Cotes Dirichlet distribution, as in the last theorem, I and J to be partitions of 1 to K. If AJI has all its elements to be 0, exactly the same condition here, AJI has all its elements to be 0, then for any X in Rk such that X is not uniformly 0, Xi given Xj minus this normalizing mean vector has a Pearson-Cotes Dirichlet distribution again. So that means the conditional distributions are also Pearson-Cotes Dirichlet. This is a marginal Pearson-Cotes Dirichlet. This is the conditional Pearson-Cotes Dirichlet distribution. If alpha high has all its components equal to half and P norm is squared norm, then the conditional random vector Xi given Xj is nothing but Pearson's generalized student T distribution. So this is a particular case if I put P equal to 2 and take all the alpha i's to be half. So this is a multivariate generalization of the conditional distribution property of students T, generalized students T. So the converse result, I have given the marginal, I have given the conditional distributions. You may ask about the converse. Assume that A is an identity matrix in Rk. Then, because if A is non-negative, is a positive definite matrix, so I can always pre-multiply by A to the minus half and convert it to an identity matrix. So let X be equal to a radius multiplied by O, which is the unit simplex uniform distribution, be a LP Dirichlet random vector. It can have parameters alpha and in the pth norm. If one marginal distribution of X is Pearson-Cotes-Dirichlet, then the whole vector is a Pearson-Cotes-Dirichlet random vector. If one conditional random vector xi given xj is Pearson-Cotes-Dirichlet, then the whole vector is Pearson-Cotes-Dirichlet random vector. This result is not known in general, but it is known in the student T distribution. If I have a multivariate student T random vector, some characterizations of this type is known. If one component of a vector is student T, then the whole random vector is multivariate student T. If I take xi and xj, look at the conditional distribution, if it is student T, then the whole random vector is student T. This is a generalization of those results known for student T random vector. I'm going to talk about, in the last few minutes, some regularly varying survival function. People talk about parametric survival function, but I will introduce to you what is called as regularly varying survival function. Look at a survival function f bar, 1 minus f. If it satisfies this constraint, survival function at tx divided by survival function at t, if it is of the form x to the power minus gamma as t becomes large, t goes to infinity, gamma must be bigger than or equal to 0. When gamma is bigger than 0, the above condition is equivalent to f equal to 1 minus the survival function is in the Frechet max domain of attraction. If you work in extreme value theory, you know that this is what is called as max domain of attraction. If R has a distribution function as above, then R is said to be a regularly varying random variable. The unit Frechet distribution with parameter gamma is nothing but the cumulative distribution function is given by e to the power minus x to the power minus 1 over gamma for positive x. So I have introduced to you a family of distributions which have a regularly varying survival function leading to a regularly varying random variable. So now I explain what this has to do with the Pearson-Cotes-Dirichlet random vector. If x equal to RAO is a LP Dirichlet random vector with A is non-singular, then I can show that x is a regularly varying random vector if and only if the random radius r is a regularly varying random variable. Please remember, this is a regularly varying random variable in univariate case. That is the constraint that is pushed on the mixing random variable r, which is a positive random variable. If it has a regularly varying survival function, if and only if it has a regularly varying survival function, then this x is said to be a regularly varying random vector. So when x is student T random vector, then x is regularly varying follows automatically because a student T random vector is a particular case. And I can prove such general properties. And I can put some fact. The conditional distributions of students T random vectors are again student T. Even when I pass to the limit, the conditional distributions remain as student. The same result holds for Dirichlet-Cotes random vectors. Recall theorem 2. So, question that arises which is unresolved. what happens with conditional random vectors of regularly varying Dirichlet random vectors. So if I take regularly varying Dirichlet random vectors, look at the conditional random vectors, what can I say about it? And that is not something that is still known. So one of the things that I can talk about is approximation of conditional distributions. And approximation is a limiting distribution. And all this is possible because of the stochastic representation I gave. So take I to be equal to 1, j to be equal to 2, bivariate case. x1 and x2 is a LP Dirichlet random vector. Alpha 1 and alpha 2 are gamma parameters. P is the norm as positive constants and a non-singular matrix A, and its off-diagonal element A21 has to be 0, remember. So suppose x1 is regularly varying with index gamma positive, then I look at the conditional random vector x1 given x2 is such that if I look at this as a sequence of random variables, x1 given x2 equal to u and b has a limiting distribution which is Pearson-Cotes-Dirichlet in 2 dimensions. And that is the only thing that we can prove in this case. More general questions remain open. So, comments on theorem 4. I have not given the proof, but I want to make some important comments. Reduced to elliptically symmetric random vectors, theorem 4 states that conditional limiting distributions of regularly varying elliptically symmetric random vectors can be approximated by student T distribution. This has implications to inference. For general regularly varying Dirichlet random vector, even when the distribution associated with the radius r bigger than 0 is not known, the conditional distributions can be approximated by Pearson-Cotes-Dirichlet distribution, which is completely known. So we can do multivariate regression, for example, because I know what the conditional distributions are. And I also know what its limiting distribution is. So this result can be used even in limit as the degrees of freedom goes to infinity. It is closed, and it is always Pearson-Cotes-Dirichlet distribution. So indeed, we model initially with an unknown distribution function, which, however, for large values in the conditioning event becomes completely specified. So this is usually leads to what is called as excess in distribution. This is sometimes called as excess in extreme value theory. It is called the excess wealth order in stochastic ordering, etc. Take a two-dimensional setup. Diverse statistical applications, you are interested in the joint excess random vector x1 over t, x2 over t, given x1 over t is bigger than 1, x2 over t is bigger than 1. And what you want to do is look at the joint excess. Excess here is simply x1 over t and x2 over t when t goes to infinity. C1 and C2 can be given constants. It is of interest. So if the approximating random vector has a known distribution function in this case, and I can give here. So x1 over t bigger than x, x2 over t bigger than y. I want to know what is the limiting probability when t goes to infinity. When I can write it as x to the power minus gamma h of x divided by y plus y to the power minus gamma g of y divided by x. H and g are two known positive functions. This is an approximation to the joint excess distribution. This can be used in modeling bivariate excess or bivariate maximas. So, approximation, this leads to what is called as tail indices. When x is a Dirichlet random vector, absolute value of x1 is regularly varying with index gamma, then various tail indices can be expressed in terms of probabilities involving Cotes-Dirichlet random vector. In particular, in the bivariate setup, this leads to what is called as upper tail dependence lambda can be explicitly calculated. So all kinds of intrinsic connections to a extreme value theory of and exceedances, probabilities, joint probabilities, limiting distributions, etc. arise. So I hope this exposition has given you an idea that what you see as simple connections between beta and gamma is a lot more deeper than what you realize, because that is related to uniform distribution on simplex. Uniform distribution on simplex is connected to independent exponential random variables, which when I mix, I get Dirichlet, and if I scale them, I can get a Pearson-Dirichlet-Cotes distribution random vectors, through which you can prove plethora of results, which are very general results, nothing to do specifically for multivariate normal, elliptically contoured models and multivariate T. You can prove things in very general terms. So thank you very much for listening, and I am open to questions. Any questions you have? Yes. Does anybody have any questions? Hello?
Yeah,
Good.
Are there any questions?
Yes, sir. I don't have any questions. I have some feelings, so I'd like to share with you.
Okay.
I enjoyed the talk very much, in the sense that I could see the student random vector in a very different perspective. And apart from that, you were specific, you were mentioning about the Pearson 7 distributions and all that, took me back to 60s, where we used to do all these things in the practical class with all, I don't think that people are doing it nowadays, and this Pearson system is part of the regular things. So this is something, and the one which I take as at this age, I'm not going to do anything, but I can say that any random vector, the representation is more comfortable for analysis of the random vector, as I understand. Am I right?
That's 100% correct.
Okay.
I think that quite often we emphasize on the distribution, the density, derivation of moments, etc. Let us think about student's T. What do we have as student's T? We have the standard normal distribution divided by square root of a chi-square random variable. But we also know this is independent of the denominator. So what that tells me is, if I take a normal divided by square root of chi-square and I multiply by square root of chi-square, if I take expectation, I can write it as a product, because the ratio is independent of the denominator. So it's the same in terms of gamma and beta. If I take a gamma alpha divided by gamma alpha plus gamma beta, we know it's a beta distribution with alpha and beta. But we don't make use of the fact that this is independent of the denominator. So that tells you that what you can do is you can take the ratio and think of the denominator as a random variable that's mixing the distribution. So you can give this stochastic representation. Now to derive moments, distributions, densities, it becomes a trivial exercise because it's a mixing random variable which is independent. So you give a distribution for the ratio, mixing random variable as a density, I can write in very general terms. So this is the way I imagine to give a specification for a multivariate distribution. Playing around with the integrals and densities and transformations in univariate and bivariate is easy. But once you go to multivariate, it's not so convenient. But the stochastic representation makes it convenient.
Yes. Thank you, sir.
Thank
Hope
you.
we hear more about phone from you.
Thank you.
Good evening,
Does anybody
Professor.
have any question?
Good evening, Professor.
Yes.
I would like to ask one question. As you have discussed about this extreme value theory, you talk about the limiting probability. That is, when time heads to infinity, we will check the exceedance after some point, right?
Right.
The probability, apart from this, calculating the probability value, is there is any other measure in extreme value theory we can use it? For
Actually, there is a whole plethora of measures. These are called tail index measures. And the tail index measures have been studied in extreme value theory quite significantly. But what I wanted to show here is the emphasis is not in the calculation of tail indices. The emphasis is to show that in the Pearson-Cotes-Dirichlet distribution can be used to express the joint probability of excess when t goes to infinity. That joint probability, which is of interest in extreme value theory, is nothing but a probability related to Pearson-Cotes-Dirichlet distribution. But if you look at any book on extreme value theory, including a book that I wrote with Enrique Castillo, Jose Maria Sarabia, and John Wiley and Sons, we have given whole list of extreme value indices that can be used for regularly varying distributions. And there are Pickens index, there are many indices. But what I wanted to emphasize here is that the Pearson-Cotes-Dirichlet distribution can be used to calculate bivariate extreme value probability. Bivariate excess probabilities can be calculated. That's what I have done here.
Thank you, Professor.
Thank you. Yeah.
Hello, Bala. Can you hear me?
Yes.
Can you hear me, Bala?
Yes, I can hear you.
Good morning, Bimolda from Maryland.
Yes. Good morning.
What you just mentioned in response to Dr. Krishnamurthy's comment, I don't know, let me put the volume a little bit high. It's kind of that's very nice result we normally teach at the graduate level, which is very funny also. Expected value of the ratio is the ratio of the expectation.
Yes.
That's what we normally do. It all follows from Bosch's theorem, independence, sufficiency, and all that. That's one way, but we can prove it directly also. So that's what happens. But very nice presentation. Good.
Thank you. Thank you.
Okay. I hope there are several are there to ask, but they now we have the time to the next speaker. In fact, we have a feast, a wonderful lecture from our great Professor Balakrishnan, Professor Bala.
Thank you.
Thank you, Professor Bala, for your support, and thank you so much for to our youngsters. No doubt it will be helpful to our youngsters on the go. In fact,
Thank
there
you.
are several from different parts. Now let us go to the next speaker. I think Neha is there ready to introduce the speaker. Just a word, please, and invite him.
Okay, sir. Warm greetings to all. I take this opportunity to invite Dr. Devendra Kumar, Associate Professor of Department of Statistics, Central University of Haryana. He did his PhD in Statistics in 2012 from Aligarh Muslim University. He was awarded Best Researcher in 2021 for Sciences and Engineering. Professor Devendra Kumar is also a life member of Indian Society for Probability and Statistics and Kerala Statistical Association. It's an honor and a privilege for us, sir, to have you here with us today. Once again, I invite Dr. Devendra Kumar to present on the topic Alpha-Powered Transform Family of Distributions, Properties, Estimation, and Application. Over to you, sir.
Thank you, Neha.
Okay, welcome.
A very good evening to the Indian participant and a very good morning for the participant from abroad. First of all, I am very thankful to the Professor Satish Kumar, chairman of this international workshop, for inviting me to deliver a talk in this international workshop on distribution theory and its application. Myself, Dr. Devendra Kumar, Associate Professor, Department of Statistics, University of Haryana. I am going to give a talk on the alpha power transform family of distribution, properties and estimation. I think my slide is visible.
Yes, sir.
Yeah, it is coming. Now it is coming.
And a very good morning, Professor Bimal Sinha. Yes.
Good morning, Devendra Kumar. Nice seeing you.
Very good morning. So a new method for generating the distribution, that is alpha power transform family of distribution, first introduced by Madhvi and Debashish Kundu in 2016. So adding an extra parameter to existing family of distribution, a very common in the statistical distribution theory. Often introducing an extra parameter bring a more flexible to the class of distribution function, and it can be very useful for data analysis. So a lot of statistician introduced the a lot of distribution for adding the extra parameter. For example, Madhulkar and Srivastava 1993 proposed a method to introduce the extra parameter to a two-parameter Babel distribution. And the two-parameter Babel distribution has one shape parameter and one scale parameter.
Excuse me, the presentation is not on the screen. Excuse me, the presentation is not on the screen.
Sorry?
The presentation is not seen.
So in my talk, the first is alpha power transform generalized exponential distribution, and another one is alpha.
Dr. Devendra Kumar, please.
Yes,
The
my slide is visible, sir.
presentation is not visible. You have shared the screen, but the slides are not visible yet.
Okay.
Now you can go to the slides, I think, or open. Yeah. Yeah, now it is fine. Now it is
Yes,
fine.
it is visible.
Yeah, now visible and it is clear.
Okay.
And go ahead.
Thank you.
You're welcome.
And another one is Madhulkar and Marshall Olkin in 1997 proposed another method to introduce the additional parameter. So in this talk, I have present some distribution, that is alpha power transform generalized exponential distribution, alpha power transform inverse Lindley, alpha power transform extended exponential, and alpha logarithmic transform Jalaj exponential distribution, and alpha logarithmic transform Bimal distribution with applications. So first is alpha power transform Jalaj exponential distribution. In this section, we propose the 3-parameter distribution referred as a alpha power transform Jalaj exponential, using the similar idea to Madhavi and Kundu in 1996, which contains some special submodel such as exponential, exponentiated exponential, and Gupta and Kundu 1999 and 2007, and truncated Gumbel distribution. And we are motivated to introduce the alpha power transform Jalaj exponential distribution because it contains number of apportioned from known lifetime submodels. It can be capable of modeling monotonically increasing, decreasing, constant Bartók and upside down Bartók hazard rates. It can be viewed as a suitable model for fitting the skew data, which may not be properly fitted by another common distribution, and can also be used in the variety of problems in different areas, such as public health, biomedical studies, environmental studies, and industrial reliability and survival analysis. And in this particular distribution, one real data application shows that the comparable compares which other competent lifetime distribution is modeling lifetime data. So we describe the model. If fx is absolutely continuous distribution function with the probability density function fx and capital Fx is the cumulative distribution function. So equation 1 is the baseline distribution, which is introduced by Devashish Kundu. Sorry, sir. Hello. Hello. Sir, am I audible?
Yes, sir, audible, sir.
Yeah, audible.
Okay.
Audible. Please mute others, those who are not. No, please. So you can continue, sir.
Okay. So this is the alpha power transform family of the distribution, which is represented by equation 1. It is clear that alpha is not equal to 1. That fx is the weighted version of fx, where the weight function is wx equal to alpha power fx. Thus, the fx can be written as in equation 3, and where wx alpha is the non-negative and expected value of wx alpha like equation 4. So we introduce the model that is alpha power transform Jalaj exponential. A random variable x is said to have a alpha power transform Jalaj exponential distribution, and its probability density function is given by equation 5. If alpha is not equal to 1, that is called alpha power transform Jalaj exponential distribution. If alpha equal to 1, then this family of distribution reduced to the Jalaj exponential distribution. So, and the cumulative distribution function is given in equation 6. And the hazard rate of the alpha power transform exponential distribution is given in equation 7. A random variable x that is follow the distribution 6 is denoted by x alpha power transform Jalaj exponential distribution. And there is a sub model of this distribution. If alpha tends to 1, then x tends to the exponential distribution proposed by Gupta and Kundu in 2001. If alpha tends to 1 and beta equal to 1, then x reduced to the exponential distribution. And if beta equal to 1, then x means alpha power transform exponential Jalaj exponential distribution reduced to alpha power exponential distribution proposed by Madhavi and Kundu in 2016. If x follows alpha power transform Jalaj exponential distribution, then x tends to 0, then fx is approximately 1 minus e to power minus x alpha, and x tends to infinity, fx is exponential. And equation 8 represents the quantile function of the alpha power transform Jalaj exponential distribution. In particular, the first 3 quantile q1, q2, q3 can be obtained by setting p equal to 0.5 in equation 8, and p equal to 0.5, that is median, p equal to 0.75, that is third quartile. So in the this is the graphical representation of the PDF. In figure 2, the various graphs of the PDF, the hazard rate function for the alpha power transform exponential distribution. Distribution for different parameter value where the scale parameter lambda equal to 1. These plots shows that the PDF can be right skewed, approximately symmetric, or reverse J-shaped. The plot 2 indicate the hazard rate function of the alpha transform exponential generalized exponential distribution. The figure 2 indicate the hazard rate function of the alpha is very flexible. It can be having increasing, decreasing, upside, downward, downwards, or bottom flow rate function. And in this slide we use the some properties of alpha power transform generalized exponential distribution. That is lemma 1. Let x follows alpha power transform generalized exponential distribution. If beta less than 1, then x equal to 0 is a model point, and it's unique when alpha is less than 1. Furthermore, if beta is greater than or equal to 1 or alpha is greater than 1, then x equal to x naught is a model point where x naught is the solution of the equation 9. So there is a corollary. If beta equal to 1, the limit x tends to 0 if x equal to 0, which implies that x equal to 0 cannot be model point. In this case, the mod is the solution of the equation kx equal to 0. And when beta equal to 1, it is easy to show that the solution of kx equal to 0 in equation 9 are x1 equal to 0, x equal to lambda e power minus 1 log alpha. However, x2 is defined only when alpha is greater than e. Therefore, if beta equal to 1, the alpha power transform generalized exponential is unimodal, and the mode is at x equal to 0 when alpha is less than or equal to e. And at x is 1 by lambda log alpha when alpha is greater than e. And remark, if hazard rate and survival function of x are denoted by hx and survival function sx respectively, then from equation 10 alpha equal to 1, the hazard rate function can be written as in the form of equation 10. It follows that the hazard rate alpha power transform and h of x is increasing function of all x for all alpha is greater than 1, and it is a decreasing function of x for all alpha 0 less than alpha less than 1. And we obtain the moments of the alpha power transform exponential distribution. The equation represent the generalized exponential distribution, and Gupta and Kundu in 2001 define the distribution of the generalized exponential distribution. They also shows that expected value of the nth moment of the generalized exponential distribution is denoted by this, and the moment general function of y means generalized exponential distribution, that is given by the equation 12. Now the nth raw moment of the alpha power transform generalized exponential distribution can be written as, with the help of the Gupta and Kundu in 2001, we can easily calculate the moment of the alpha power transform generalized exponential distribution. So where alpha by follows exponential to exponential, that is alpha p plus 1 lambda on using the equation 12. We find easily the nth moment of the generalized alpha powered transform generalized exponential distribution in the form of equation 13. So note that equation 13, it is obvious that mu1 exists for all alpha greater than 0 and integer value of the beta. In fact, it can be shown that mu1 exists for all alpha beta greater than 0. Similarly, we can easily find the moment general function of the alpha power transform generalized exponential distribution can be written as equation 14. So we can easily find out the mean and second moment, and also find out the variance of x by using the formula expected value of x square minus expected value of x whole square. These are the moments of the alpha power transform generalized exponential distribution for different value of the parameter. In the third column is the mean, variance, coefficient variation, skewness, and kurtosis. So in this table, we can see that we increase the value of the alpha and beta, the mean and variance are also increasing. And also we increase the value of the alpha and beta, and decrease the skewness and kurtosis. So we can also easily find out the conditional moment of the alpha power transform exponential generalized exponential distribution by using this formula expected value x power x greater than x, or this equal to 1 upon survival function into j and x, where j and x is denoted by this one, x to infinity by n f by dy. So the jn, put the value of jn in this equation, we find the conditional moment of the alpha power transform generalized exponential distribution, and also find the mean residual life function in terms of the first condition moment, that is n equal to 1 in equation 15. We find that easily mean residual life of the alpha power transformed exponential distribution, and we can easily find out the mean deviation about mean with the help of the conditional moment. Conditional moment del mu equal to 0 to infinity absolute value of x minus 1 fx dx. So and we find the j1 by using the jnx in equation 15, and we also find out the stochastic ordering, that stochastic ordering x less than y if f of x greater than equal to f of y for all x. So we can easily find out the stochastic ordering, and we can obtain the Shannon entropy, that is expected value of minus log of fx, and given by equation 60, and easy to check that expected value of 1 minus e power lambda in equation 17, and 1 minus e power lambda given by equation 18. The substituting equation 17, 18, equation 16, we obtain the Shannon entropy. And also we find the distribution of the order statistics, that is jth order statistics, given by this formula. This is the formula for the distribution of the jth order statistics, and we substitute the value of the probability density function of alpha power transform generalized exponential distribution and cumulative distribution of alpha power transform exponential distribution. We find the distribution of the jth order statistics of alpha power transform distribution in the equation 20, and this is also the CDF of the jth order statistics of the alpha power transform generalized exponential distribution is given by equation 21, and also find out the kth moment of the jth order statistics. This is the formula for kth moment of the jth order statistics in equation 22. And we consider the method of estimation, that is method of maximal likelihood estimation, that x1, x2, xn be a random sample of size n from equation 5. Equation 5 means the probability density function of alpha power transform generalized exponential distribution. So the log likelihood function of equation of the alpha power transform exponential distribution given by 23. For the age of the notation, we will denote the first partial derivative of equation 13, that is L alpha beta. We differentiate partial differential equation 23 with respect to the parameter, that is alpha beta lambda. So the first derivative we have the equation 24, and with respect to beta 25, and derivative with respect to lambda in 26. Though the maximum likelihood to estimate alpha hat, beta hat, lambda hat of alpha beta lambda are obtained by solving the non-linear system of equation, that is equation 24, 25, and 26. And say another method of estimation, that is method of maximum product spacing. Let x1, x2, xn are the order statistics of a random sample of size n from the alpha power transformed exponential distribution. Let us also define the uniform spacing of a random sample from the alpha power transform generalized exponential distribution, that is this one, di equal to f of xi and alpha beta lambda minus k of xi minus 1, where f of x naught and equal to 0 or this equal to 1. So clearly sum of this is di equal to 1. So this method is first introduced by the Chen and Mn in 1983. The maximum product spacing estimators of the parameter alpha beta lambda are obtained by minimizing the geometric mean of the spacing with respect to alpha beta lambda. This is the equation 27, or equivalently minimizing the function h alpha beta lambda, that is 1 upon n plus 1 summation I running from 1 to n plus 1 log di in equation 28. So the estimators alpha beta lambda of the parameter alpha beta lambda can also be obtained by by using the partial derivative of equation 28. With respect to alpha beta lambda, where delta xi1 alpha beta lambda is given by equation 32, and lambda 2 delta 2 is 33, and delta 3 is given by equation 34. So change in M in 1983 shows the maximizing H as a method of parameter estimation is the efficient as MLE estimation, and MPS estimator are consistent under more general condition than the MLE estimators. And another method I have used, the method of ordinary and weighted least square estimator. The least square estimator and weighted least square estimator were proposed by Swan et al. 1988. So it is known that expected value of the cumulative distribution function ith order statistics equal to I n plus 1, and variance of this equal to this one, that is given in equation 35. So the ordinary least square estimator alpha beta lambda of the parameter alpha beta lambda are obtained by minimizing S alpha beta lambda, that is summation I running from 1 to n f of ith order statistics minus k I upon n plus 1 whole square, that is given in equation 36. So these estimator can also be obtained by solving the non-linear equations, where delta 1, delta 2, delta 3 are given equation 32, 33 and 34 respectively. And the weighted least square estimator alpha beta lambda hat of the parameter alpha beta lambda are obtained by minimizing the function w, that is I running from 1 to n n plus 1 whole square n plus 2 divided by I and minus I plus 1 f of ith order statistics cumulative distribution of the ith order statistics minus k I upon n plus 1 whole square, that is given in case of equation 37. So these estimator can also be obtained by solving the nonlinear equations. So equation that is 38 with respect to alpha, beta and lambda given equation 38, 39 and 40, where lambda, delta 1, delta 2 and delta 3 are given in 34, 33 and 34 respectively. And we use these method. So we use the competency of this method, these methods via the numerical computation. In this section, we evaluate the performance of the estimation method through the small simulation study. Through the simulation study, we also illustrated the applicability of the alpha power transform generalized exponential distribution using a real data set. So in this section, we evaluate the performance of the different method of estimation discussed in the previous section. In the simulation study, we generated the sample n equal to 1000 sample of alpha power transform generalized exponential distribution in 3 cases, that is alpha equal to 0.5, beta equal to 2, lambda equal to 1. And another case is alpha 2, beta 0.8, lambda 1, and alpha 2, beta 2 and lambda 1. So these absolute bias and mean square error of the point estimator are obtained to evaluate the performance of the estimation method. The results are presented in table 2 to 4 respectively. The average interval length of the coverage rate of 95% confidence interval, including the boot P and boot T confidence interval for different parameter value, are given in table 5 and 6. So the table in table 2, average bias of the estimate alpha beta lambda and their associated MSE in parentheses. So from table 2 to 4, we observe that all the estimators show the property of the consistency, that is the MSE decreases as sample size increases. So MSE is given in parentheses. So first alpha equal to 0.5 and n equal to 10. So we increase the size and the MSE is decreasing. Also, the bias of alpha hat, beta hat, lambda hat decreases as the sample size n is increases. So ML is the bias of the alpha beta lambda, it decreases as sample size increasing for all the method of the estimation. And the bias alpha cap generally increase where the increasing alpha for any given alpha and n for all the method of estimation. Furthermore, all the method of estimation produce the these are the average bias and estimate alpha beta lambda for different value of the parameters. So in general, the result in table 2 to 4 shows that MLE produced the good result for estimating the parameter alpha and best result for estimating the parameter beta and lambda. So in table 5 shows that the average length of the confidence interval for alpha is quite large. This due to fact that the standard error of the estimating parameter alpha is higher than compared with other two parameter beta and lambda. So the, table 5 to 6, the average length of the coverage rates, and in this distribution, the last section is the data analysis. So in this section, the alpha power transform distribution used to model the daily ozone measurement in the New York from May to September, and this data is discussed by Nadraja in 2008 and Wilside et al. In 2011. For the sake of the comparison, we also fit the data for modified Bibble distribution, Lay et al. 2003, and exponential Bibble and generalized exponential extended generalized gamma distribution. So the maximal likelihood estimator method used to estimate the distribution parameter, the maximal likelihood estimate, Akai information criteria, tested and Kolmogorov test, and p-value of the KS test are presented in equation in table 8. So these are the other competent model, that is alpha power transform, the generalized exponential, that p-value is very high as compared to other distribution. So we can say that our model is fit to this data set. And the table 9 represent the estimate of the parameter of the confidence interval for daily. Sorry. Yes. P-value is not visible. In the last column, p-value is my slide is visible. In the first distribution, that is modified Bibble, the p-value is 3.28 into 10 to power minus 7. Yes. No, this is not fitted. This modified Bibble distribution not fitted. Modified distribution is not fitted. Our model, because p-value is very high, 0.69. Yes. So I think this model is so this model is cancelled out from this list, and we have other two models. Two model comparison comparison to the other two model. Our model is best fit for this data set. Yes, definitely. Okay. So these are the QQ plot for the daily ozone data. So our QQ plot in the figure 3 indicate the alpha power transform generalized exponential distribution, provide the most accurate fit to the ozone data set. For interested reader, the parameter of the alpha power transform generalized exponential distribution are estimated by the apportionment method. The estimate of the parameter along with the boot P and boot T confidence interval are given in table 9. This is the table 9, the boot T and boot P. So these are the histogram for fitting the density function of the ozone data. So the ozone alpha power transform generalized exponential, this is a pink line. So we can say that our distribution best fit. So next distribution, the alpha power transform inverse cylinder distribution. So we introduce the new gender distribution, that is alpha power transformed inverse cylinder distribution. that provide the better fit than the inverse linear distribution and some of its known generalization. The new true inverse linear distribution as a specific. The various properties of opposed distribution, including expression for mode, movement, system movement, mean residual life, one-point Lorentz curve, entropy, stochastic sorting, strength relativity, and order statistics. So Sharma et al. Sorry. Sharma et al. Such the inverse linear distribution with the principal function given by g of x equal to with cumulative distribution is this. So we introduce the distribution that is alpha inverse linear distribution by using the baseline distribution that introduced by Kundu, Madhvi and Kundu in 2016. So our new model in equation 41, where x is greater than 0, alpha lambda is also greater than 0, corresponding the survival function given by equation 42. And the survival function is given 43 and hazard rate function given by 42. So in this section, we discuss the shape of the characteristics of the PDF and hazard rate function. The PDF and hazard rate function of the alpha power transform inverse linear distribution follow the following end behavior: f of 0 equal to minus f of infinity, that is 0, h of 0, that is equal to 0. So the proof is not discussed. This is the graphical representation of the density function and hazard rate function. So figure 5 shows the various curve of the PDF of the alpha power transform inverse linear distribution with various value of the parameter alpha and lambda. Similarly, one can show that the hazard rate function of the alpha power transform linear distribution is unimodal. Figure 6 shows the various curve of the hazard rate function of alpha power transform in inverse linear distribution with various value of the parameter alpha and lambda. So in the special case, let x follows alpha power transform linear distribution with parameter alpha and lambda. If alpha tends to 1, then x reduce the inverse linear distribution. This proposed by Sharma et al. In 2015. And alpha equal to e, then x reduce the inverse linear Poisson distribution in the form of this equation. And we find out the mathematical properties, that is moments. So first of all, we discuss the lemma. That is fx and small fx, the probability density function of alpha power transform linear distribution, and capital Fx, the cumulative distribution, given by 41 and 42. So A is greater than 0, B is greater than 0, and C greater than 0, and delta is also greater than 0. So we define K of A, B, C lambda equal to this one, where we have the K, A, B, C lambda. After some mathematical calculation, we find the K, B, C like this one. And proof is not discussed here because there are some lot of mathematics. So by using the K, A, B, C, put the value of this in equation, this we find that the expected value of x ki power n, that is nth moment of the alpha power transform inverse linear distribution, is given by this, where K alpha beta lambda is defined this one. So, and also we calculate the variance by using the formula expected value of x square minus K expected value. If we put n equal to 1, we find the mean. If we put n equal to 2, we find the second moment. So by using the formula of expected value of x square minus expected value of x whole square, we can easily find out the variance of the alpha power transform inverse linear distribution. So the central moment BR and cumulate KR of x means alpha power transform linear distribution can be determined from the equation 48 as mu r equal to by using this formula. So we can easily find out the skewness kurtosis also by using the formula gamma 1 equal to K3 upon K2, 3 by 2, and kurtosis gamma 2 equal to K for K2 square. So the nth incomplete moment of alpha power transform linear distribution can be easily found out by using this formula: expected value xn x less than by 0 to infinity x e power n fx dx. And by applying the some mathematical calculation, we find that the m by n, that is incomplete nth incomplete movement. And lemma 2 by we have calculated the conditional movement. So with the help of lemma 2, we can easily find out the conditional movement of alpha power transform inverse linear distribution. So if c is an integer, then 49 equation 49 can be simplified in this form. And the application of the conditional movement is the mean residual life in the lab testing experiment. The expected additional lifetime given that an item has survived until time x is called mean residual life. The mean residual life function of the alpha power transform inverse linear distribution can be written by using this formula, where L alpha lambda can be obtained from equation 52. That is the lemma 2. Lemma 2 is the lemma 2 is this one. By using this formula, we can easily find out the mean residual life. And also we can easily find out by using the lemma 2, we can easily find out the mean deviation about mean and median. And L moment, the sum of the other important measure useful lifetime model is the L moment due to the Hosking. It can be solved using the lemma 1 of the kth L moment. And also we can find out the moment journey function of the alpha power transform inverse linear distribution by with this expression. And alpha less than lambda, t is less than lambda, the characteristic function of phi xt, that is expectedly e power I tx, and the cumulative genetic function of x means alpha power transform inverse linear distribution, or kt equal to log of phi t, is given by this equation. This is the characteristic function of alpha power transform linear, or this is the cumulative genetic function of alpha power transform linear distribution. And also we can find out the Born-Ferroni and Lorentz curve by using this formula. Born-Ferroni, that is 1 upon p mu 0 to q x fx dx, and the Lorentz curve by using this formula. So q is the quantile function. If x has the PDF 1, by using lemma 2, one can calculate the Born-Ferroni curve alpha power transform inverse linear distribution as given by this equation. This is the Born-Ferroni, or this is the expression for Lorentz curve. And entropy is used to measure the variation of the uncertainty of the random variable of x if x has the probability density function of the alpha power transform linear distribution, and defined by this equation 50. This for delta is not this question. So
probably with Devendra Kumar, Dr. Devendra Kumar. So let us wait a few minutes. Let us talk to him after the talk.
Hello.
Hello, sir. He has some network issues, Paul. Sir. I'm trying to contact him by this. Let us wait some more time.
How are you? Hello, Dr. Satish? Hello?
Yes,
You know what is happening? It's nothing coming. Hello?
sir, I am contacting him.
Huh?
What happened to him?
Uh,
I'm contacting him. I'm calling him. Some network issues may be there with the Dr. Devendra Kumar. He joined. He joined, sir. He joined. Kalyan, sir, he joined. Okay. What happened? There is some network issues.
Devendra sir, you are on mute.
You are, yeah.
I
Please.
think there is some network issue. Yes, my slide.
Yeah. Yeah.
Okay.
Yeah, now slides are not visible. And now it is visible. Can make it full
Yes,
screen.
visible?
Yeah, it is visible. Yeah, now it is fine.
Okay.
I think, yeah.
We are in, I think,
We are-
method of estimation.
We are waiting some more, a few minutes back, I think,
In the
3-4 minutes.
approximate confidence interval. or method of likelihood estimation?
Yeah, yeah. You can continue from there. Yeah.
Okay. So we find the unknown parameter by using the method of maximum likelihood estimation. So equation 54 is the log likelihood function of the alpha power transform inverse linear distribution. To obtain the likelihood equation for unknown parameters, we differentiate 15 partially with respect to alpha and lambda. So we get the two non-linear equations. These non-linear equations by solved by the Newton-Raphson method by using the R software. And we also calculate the approximate confidence interval in this expression. And these are the derivative of the information matrix, Fisher information matrix, with respect to lambda, alpha, and lambda. And these are the approximate 101 minus tau % confidence interval for parameter alpha and lambda. And we use the Monte Carlo simulation method. So in this section, we investigate the performance of the MLE of the alpha power transform linear distribution of the parameter by using the Monte Carlo simulation. The simulation study repeated 1,000 times, each with sample size, the different sample size than 25, 50, and 100. Under the scenario, alpha, there are the alpha lambda equal to 2, alpha equal to 0.5, 0.8, 0.5, and 2.5. And second is lambda equal to 4, alpha 0.5, 0.8, 0.5, and 2.5. In table 1, present the average value of the estimate, mean square error, and approximate confidence interval of the MLE of the parameter alpha and lambda for each parameter combination and different sample size. And from this is the table 10, the average value of the estimate and MSE in the parenthesis. From the result in the table, we can conclude that the maximum likelihood method performs well for estimating the alpha power transform inverse linear parameter. In addition, the approximate confidence interval length decreases. The confidence length decreases as the sample size increases in all cases. Also for fixed n and lambda, alpha is decreasing, MSE of lambda decreasing, and the confidence length of the lambda increases for fixed n and alpha, and lambda increases, MSE of alpha increases. So we use this is the average value of the estimate for different value of parameter and different cases, and use the inverse CDF method for generate the random variate of equation 52. 52 is the cumulative distribution function of the alpha power transform linear distribution. For the distribution, CDF cannot be obtained by explicit form. For this reason, we propose the Newton's method for solving the inverse CDF of alpha power transform linear distribution. We use the following algorithm to generate the random sample. These are the set the value of n, alpha, and lambda, and initial value of x naught. Generate u, use the uniform 0, 1, and we use the Newton method update the x naught by this formula. So we find the table of the average value of the estimate and MSEs and class interval. And next, we apply the two data set for this model. The first data set, the first data set represent the I think some is missing, and second data represent the survival time in days of 17 Genova pig infected with the table versely. The data were observed, the reported by this one, and data are obtained this. These are the data 1 and data 2. We compare the fits of the alpha power transform inverse linear model with the inverse linear distribution, generalized inverse linear distribution, exponentiated generalized inverse linear distribution, and exponential inverse linear distribution, and inverse Weibull. These are the competent model. We estimate the model parameter by using the maximum likelihood method. We compare the goodness of fit model using -12, where L denote the likelihood function evaluated the maximum likelihood estimate. Kolmogorov, case test, Akai information, and Bayesian information, BIC. So these are the probability density function of the other competent model: inverse Lindley, generalized inverse Lindley, exponential inverse Lindley, and exponential generalized inverse Lindley distribution or inverse Weber. So equation in table 13 and 11 and 13 list the MLEs and corresponding the standard error of the parenthesis of the parameters, and the value of -12, KS, Akaitis, BIC are displayed in table 12 and 14. Among all other competitive model, it is to be noticed that these are the MLE and standard error for data 1, goodness of fit of data set data 1, and table 13 is the MLE and standard error of data 2, and table 14 the goodness of fit of the data 2. So this is the relative histogram and the fitted densities, and the fitted and empirical survival function of data 1. And this is the relative histogram and fitted density and the fitted empirical survival function of data 2. So we can see easily that our model is best fit and the other competent model for these data sets. So this is the second distribution, that is, first is the alpha power transform generalized exponential, second is alpha power transform inverse linear distribution, and third, by using the same method, that is the baseline distribution that is introduced by Madhvi and Kundu in 2016. First is alpha power transform generalized exponential, second one is alpha power transform inverse linear, and third is alpha power transform extended exponential distribution. So and in this distribution, let X follow the extended exponential random variable with parameter alpha and lambda with the probability density function given by equation 55 and 56. Here alpha and beta and lambda are parameter.
Kindly mute others, please. Dr. Devendra Kumar, you can continue.
ഒരു മെസ്സേജ് നോട്ട്
Dr. Devendra Kumar, left hand.
Network issues, is it?
There may be network issues, sir. I'm calling him because sometimes he will not know whether it affected the network. That is right.
Hello.
Hello. There is, it is you left. Okay, you joined. Okay, please. Hello, doctor. Hello.
Hello, am I audible, sir?
Now it is audible. there may be network issues in your place, isn't it?
Sir, this side. There is some difference.
Okay. Whether it is here or not, I don't know. I think now you can continue, because you can share the slides once again and continue it. Hello, can you hear me?
Hello.
Yes, yes, we can hear you now.
Okay.
Now we can continue. You are weak, I think so.
Internet, some disturbance from my side.
Okay. Don't worry. Okay, you can continue. Why I called you because sometimes you will not know while presenting these things.
Yes.
Okay. That is why I call you via WhatsApp. You will be not disturbing your other way. Okay, Dr. Devendra Kumar, please continue. You can share the slides once again.
Okay, yes, sir.
Some participants are asking the PPTs or the slides. Okay.
No issue. I share you.
Okay.
I share you the
Anyway,
slide and
yeah. Okay, very good. Please, now it is coming. You can go to the slides.
Okay.
Yeah. Now we can make it full screen.
Sir, next.
Yeah, if possible.
Next distribution, we use the same, the baseline distribution. Sir, am I audible and my screen visible?
Yeah, audible.
Okay.
Now audible and the slides are visible.
Yes.
It's fine.
Okay.
Please continue.
So we use the same distribution. We introduce another distribution that is called alpha power transform extended exponential distribution with applications. So in this section, we use the extended exponential distribution. We get by using the Madhvi and Kundu baseline distribution, we get the extended exponential distribution. So definition and properties of this distribution: let x follows the extended exponential random variable with parameter beta and lambda. That is given by equation 55, and the probability density function of the extended exponential distribution, and the equation 56 represent the cumulative distribution function of the extended exponential distribution. So now we introduce the notation alpha power transform exponential distribution, that is APTED distribution. If fx is absolutely continuous distribution function with the probability density function fx and cumulative distribution function capital Fx is also an absolute continuous distribution function with PDF. This one equation 57 is the alpha power family of distribution that is proposed by Madhvi and Kundu in 2016. So it is clear that alpha is not equal to 1, then it is a weighted version of fx where the weight function is defined in 58 and the probability density function or the weighted function is given by 59, and where wfx is non-negative, this is expected value of wx is given in equation 60. So a random x is said to have a alpha power transformed extended exponential distribution if its probability density function PDF is the form of this equation, that is equation 61. If alpha is not equal to 1, then this is called alpha power transformed extended exponential distribution, and if alpha equal to 1, that this is called the alpha power transformed exponential distribution reduced to the extended exponential distribution, which is the present equation 61. And equation 62 represent the cumulative distribution function of the alpha power transform extended exponential distribution, and equation 63 represent the hazard rate of the alpha power transform generalized extended exponential distribution. So there are some special cases. Alpha tends to 1, then x tends to extended exponential distribution. This is proposed by Nadaraj and Hagai in 2011. If alpha tends to 1, beta equal to 1, x reduced to exponential distribution. X means alpha power transform extended exponential. If beta equal to 1, then x reduced to alpha power transform exponential distribution proposed by Madhvi and Kundu in 2017. So these are the some result given equation 64, 65, and 66. So it is clear that equation 65 is the alpha approaches 1, x behave like an extended exponential distribution, and alpha is increases, it behave like x2. So figure 9 and 211, these are the graphical representation. Alpha plot of the hazard rate, alpha power transformed exponential distribution, various value of alpha and parameter, and figure 10 is also hazard rate, and figure 11 is also the hazard rate of the alpha power transform extended exponential distribution. The plot in figure 19 to 11 indicate that hazard rate function of the alpha power transformed extended exponential distribution is very flexible. It can be behave increasing IFR, decreasing DFR, constant, upside down, bathtub, or bathtub flow rate function. One of the advantages of the alpha power transformed extended exponential distribution over the extended exponential distribution is that a letter cannot model phenomenon showing the bathtub and upside down bathtub flow rate. And these are the some properties of alpha power transform distribution. That's the shape of the density function and moments. Equation 69 is the probability density function of the extended exponential distribution. So Nadaraj and Hagai 2011 shows that this is the kth moment of the extended exponential distribution given in equation 70. Now the kth row moment of the alpha power transform extended exponential distribution can be written as expected value xk equal to 0 to infinity xk fx dx. This is the general formula for calculating the moments. That is alpha upon beta, beta lambda divided by alpha minus 1 into expected value of x power k. By is distributed extended exponential distribution that is introduced by Nadaraj and Hagai, and also they obtained the kth moment of the extended exponential distribution. So by using this formula, we easily find out the moment of the alpha power transform extended exponential distribution, which is presented shows in the equation 71. Note that from equation 71, it is obvious that mu k exists for all alpha greater than 0 and integer value of the beta and lambda greater than 0. In fact, that it can be shown that mu k does exist for all alpha, beta, and lambda greater than 0. Similarly, the moment genetic function of alpha power transform extended exponential distribution can be written as this one. This is the moment genetic function of the alpha power transform extended exponential distribution, and variance skewness kurtosis can be obtained by using these formula. So from table 15, we reported the mean, median, variance skewness of the kurtosis. So we see that in equation 15, table 15, if we increase the value of the parameter beta and alpha, we increase the mean and variances, mean, median, and variances, and we increase the alpha and beta, the skewness and kurtosis decreases. So we also obtained the alpha power transform exponential distribution, that is conditional moment, given equation 73, and mean residual life, and also we calculate the mean deviation about mean and median, and also calculate the Bonferroni curve, Lorentz curve, Gini index, Renyi entropy by using these formulae. So we can, by using the proposition 1, we can easily find out the Bonferroni curve, and proposition 2, Lorentz curve, and X as the probability density function, the Renyi entropy can be calculated by using the formula 74. And the proof of this Renyi entropy given in proposition 3, that is given in equation 75. So also we calculate the stochastic ordering. Proof of the stochastic ordering is here, and also we calculate the strength reliability of the alpha power transform extended exponential distribution. This is the expression for the stress strength reliability, that is R equal to log alpha divided by alpha minus 1 whole square. And in this section we also calculate the order statistics. This is the formula for the jth order statistics. And first we calculate the distribution of the jth order statistics of the alpha power transform exponential distribution. And this is the CDF of the alpha power transform extended exponential distribution. And also we calculate the kth moment of the jth order statistics or alpha power transform exponential distribution by using this formula. And we estimate the unknown parameter by using the method of likelihood function. So here we obtain the MLEs of the parameter alpha power transform exponential extended exponential distribution. Suppose x1, x2, xn be a random sample of size n from alpha power transform extended exponential distribution with PDF 61. So the log likelihood function given by equation 77. And log likelihood equation becomes by differentiating partially with respect to the parameter. We find the equation 79, 80 and 81. And also we calculate the asymptotic confidence interval. And we conduct the simulation study. In this section, simulation study has been carried out to illustrate the behavior of the MLE in terms of the sample size n. We consider the value of 0.5, 0.2 for the parameter alpha, 0.5 and 2 for the parameter beta, 1 and 2 for lambda. For total of 16 parameter combination, different sample sizes and 1000 replications, we obtain the average value of the absolute bias, mean square, error and approximate confidence interval. The simulation results are reported in table 16. This is the table average bias of the estimate alpha, beta, lambda and their associated MSE in the parenthesis for maximal likelihood estimation. So in this simulation result shows that the MLE of the unknown parameter are quite close to the true value of the true values as sample size increases. So this is the 10, 25, 100, 2000, 200. And another combination 10, the alpha is 2 and beta is 2 and lambda is 1. And there is another combination alpha 2, beta 0.5 and lambda is 1. So we can easily find out with the help of the simulation study, the average bias estimator and their associated MSE of the maximal likelihood estimation. So in the next, we also take the two real data set in this section. The first real, the remission, time remission in month of the random sample of 128 bladder cancer patient, C. Lee and Bung in 2003 and the Lemot 2013. The data set as follows, this one. And second data set represent the survival time in days. 72 Genoa pig infected with virulent tuberculosis and reported by this one data set are this. So by using the maximal likelihood approach, alpha power transform extended exponential distribution is the fitted to both the data set as compared with other competent model, namely Bibble distribution. We have the other competent model, that is Bibble, generalized exponential, distribution exponential distribution and exponential Nadaraj-Hagai distribution. So the maximal likelihood estimation of Hagai information criteria, test strategy AIC, BIC, KS test and p-value of the KS tests are presented in table 17 and 18, the data set first and second respectively. So these are the probability density function of the competent model just Bibble, generalized exponential, Marshall-Orkin extended exponential distribution and exponential Nadaraj-Hagai model. So in table 17, The result in 17 and 18 indicate the alpha power transport distribution has the smallest KS value. Empirical and theoretical density of CDA plot are presented in figure 12 and 15. These are the empirical for data 1 and data 2 respectively. The QQ plot. The QQ plot of the figure of the data set 1 and data set 2 are given. Figure 13 for data set 1 and 14. And 14 is the model fitted by the MLE of the data first of alpha power transport. So we see in this graph, our model is fit and other competent model for this data set. And these are the hazard rate, histogram plot, and empirical theoretical CDF. And this is the PP plot for data set second. And this is the histogram plot for the data set second. So these are the third, this is the third distribution that is called alpha power transform extended exponential distribution by using the baseline distribution that is introduced by Madhvi and Kundu 2016. Hello?
Yes, yes, we can hear you. Okay.
We can continue?
I think it is better to conclude because time, or if near you can conclude, briefly explain other matters and just conclude.
Okay, so in this talk, we use the baseline distribution that is called alpha power transform family of distribution. So by using this baseline distribution, we have introduced 3 distributions. First one is called alpha power transform generalized exponential distribution. Second distribution, alpha power transform inverse linear distribution. And third one is alpha power transform extended exponential distribution. For these distribution, we have calculated the some mathematical properties like moments, conditional moment, one-Froning curve, stochastic ordering, and we also obtain the unknown parameter by using the maximal likelihood method. A method of in the one distribution, there are some other method for estimating, and also we use the real data application for competent for the example point of view, and I think these distribution, these alpha power transform, generalized exponential, extended exponential, inverse linear distribution for flexible for the new data set. And there are some query. So please.
Now let us have a discussion about it. Someone has raised. Yeah, please.
Yes. Okay. Sorry. Yes. I am listening. Okay. Mm. There is some error in your program, so please check again and again. Sometime missing in a bracket or comma. So please rewrite the program again and again. The problem is rectified.
Sir, good evening. I have a question actually. Hello, am I audible, sir?
Yeah,
Hello?
you can continue.
Yeah, okay,
It's
thank you, sir.
audible.
Yeah, thank you. Sir, my question is there are so many transformations are available for statistical distributions like TX, family, and alpha, like as you said, alpha power transformation and transmuted distributions. So I want to know the original mathematical background of this. Like, what are the references that you are going through for those mathematics? Like, why we are using only alpha power, or why we are using only TX?
There is a book for integral and transformation by Johnson and Coates.
1 minute, sir. Integral and
Transformation
okay,
by
Johnson and
sorry,
Coates.
Integral and Transformation by Cohen.
Cohen.
Yes.
Okay, sir.
Please send me a mail. I will
Okay.
send you a copy.
Thank you, sir. Sure, sir.
Thank you.
Thank you.
Sir,
Yes, you can ask Professor Gade. Hello, Professor Gade.
yeah. Thank you, Professor. Thank you. Very nice presentation, Professor Devendra Kumar.
Thank you, sir.
Namaste. And my concern is, for example, you have prepared alpha power transformed generalized exponential and exponentiated exponential.
Yes, sir.
And exponentiated exponential is the special case of generalized exponential, I think.
Yes.
For a specific parameters.
Yes.
So that is my concern. Is it a need of again studying or any other importance you found in your study? That is the one concern. And other is when you are comparing the distributions, you have compared this exponential, this transmuted distributions with normal distributions like exponentiated, Weibull distribution, and other distributions. Did you compare these four distributions for any real data?
Hello. Am I audible?
Do you find any? Yeah.
Yes, please.
Do you find any compare to study between these four distributions for any real data?
No, sir, not yet. But I am planning to compare these four distributions.
Okay. Nice. Thank you.
Any other questions? If there is no questions from the audience, in fact, nowadays we have you can contact the speaker via online or via
Yes,
email.
definitely. Yes.
Yeah, don't worry about that. His email ID is available with us as well as in the mail, also, in the online also, in his site.
Satish sir, I share you the whole presentation. So anyone want the PPT, so please send the other participants.
Dr. Devendra Kumar, you share the PDF file of the presentation, not the
Yes, yes.
PPT. Original form.
PDF file of the,
Only-
oh, yes, yes. Yes,
Yeah.
yes.
Because
Yes.
some slides are there is needs some clarity in the
Yes. Network Yes,
issue.
definitely.
That's why some participants are asking.
Yes,
Anyway,
yes, definitely. Sure, sir.
you did a very nice talk, and we are grateful to you, Dr. Devendra Kumar. Thank you so much. And we need your support and service in
Yes,
future
sir.
also.
Yes, sir. Yes, sir.
I hope today we have two excellent lectures. One Professor Balakrishnan of McMaster University, Canada, and then Professor Devendra Kumar of Central University, Haryana. And tomorrow we have two more experts. While Professor Dr. Devendra Kumar mentioning about Kundu, tomorrow you can see Kundu's
Yes.
talk. The Devasis Kundu of IIT Kanpur, and also Professor Kusubavsky, University of Nevada. Tomorrow morning, please note that tomorrow, not in the evening, but in the morning, because Professor Kusubavsky, it is convenient to, morning time is convenient to him.
Okay.
Anyway,
okay.
and also Professor Kundu also asked in that way.
Okay.
Once again, I utilize this occasion to extend our gratitude on behalf of the organizing of this workshop, as well as the all the participants gathered together. In fact, there's a good participants. Most of the time there is 100 and 101 like that. And in fact, there's a limit in this Google Meet. There is YouTube live stream also there. So several are there also. Anyway,
Sir,
please.
I am also thankful to Professor Sinha.
Thank you, Devendra. Thank you for your nice presentation.
Yeah.
Okay. Very good.
Yeah. In fact, great professors are there in the group. Professor Sinha is also supporting us in a very sincere way. And
Yes, sir.
Thank you, Professor. Let us conclude the session. Once again, giving a big clap to the speakers of today's.
Thank you, sir.
And we hope tomorrow morning, please join by 8:30 itself, 8:30, after 8:30, before 9, because it's better to get into the meet. Expecting all, and let us see you all tomorrow morning, but there in the maybe in the evening time. Professor Sinha. Yeah.
Okay, Shakesh, thank you.
Thank you so much.
organizing.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you all. Thank you all. Yeah.